This video is our sixth lesson for the derivatives unit number 3, and in this lesson we're going to look at something called implicit differentiation. Strangely enough, I'm actually going to spend the first couple of pages doing everything I can not to do implicit differentiation, just to show you why we have it and what kind of situations really require you to use it. And I'm going to also use this chance just to review the graphing of circles, because I know some of you haven't done a lot of that. So the equation for a circle is actually pretty simple. It basically just says that circles are round. It's like, yeah, no kidding, right? But the idea of them being round is that every point on the circle is the same distance away from its center. And so I can actually measure that distance, that radius, just using some Pythagoras. And that's why the equation looks the way it does. It really is a Pythagoras story. And it says x squared plus y squared for every point that's out here has to be equal to the radius squared of the size of the circle that you want. If you want to do a little transformation to it, kind of like a little Math 12 transformation issue, you could say, oh, okay, well, how about x, and then if I want to move it to the right, I could say minus a, right? Just put a number in there, squared, just following the pattern up above though, y, and then maybe minus a b, right, to move it over and up. Squared is equal to whatever radius you want squared. So this first question here, where I'm going to just use this as practice and I'm going to try to avoid implicit differentiation for a while, that's a circle because I can see it has this x squared plus y squared pattern to it, and it's equal to a radius squared. So that number here, that is actually the radius of the circle squared. So clearly for this circle, the radius is going to be a 5, and it looks like it's centered 2 over and 3 down. So the center is right here, and then it's got a radius of 5. So looking at just the edges of the circle, one edge is going to be right there. 1, 2, 3, 4. Another edge is here. 1, 2, and here. And where's our final edge? 1, 2, 3, 4, 5. We're just going to try to sketch a circle out. Now, I'm going to cheat, because if I don't, my circle will look horrible. But it's basically like that. And again, I'm going to do a little bit more cheating just while you're sketching your circle there. And if you look at it and go, whoa, it doesn't quite look round. Yeah, the actual graph paper here wasn't quite square. If you look at the little boxes there, they're not exactly square, and that's why we see that. Okay, let's just thicken this up. So there's my sketch of my circle. Okay, great. Example 2 says, can you sketch in a tangent line at x is equal to 5? Now I've then gone and scratched off x is equal to 5, and here's the reason why. If I just tell you, oh yeah, I would like you to draw a tangent line at x is equal to 5, right? At this spot. Well, I don't know, where do you want your tangent line? Do you want it here on the upper half of the circle, or do you want it down there? And it's not clear, right? It's not good enough to just give an x value anymore. This is actually something that's characteristic of questions that need implicit differentiation. So worth a note here, actually. Okay, it's quite important. It is not sufficient. It's not good enough. Oop, I should learn how to spell and get my grammar right. It is not sufficient to only specify an x value. We need an xy pair. So that's why it says, oh, let's do it at the point 5, -7. Ah, okay. That must be this point right here. So 5 over, sure, they both were, and then -7. Ah, yeah, if I have that pair of numbers there, then I know where you want this tangent line drawn in. So, okay, yeah, sure, here comes your tangent line. I guess it's going to look, something kind of like that, okay? Now, calculus should help you find the slope of that tangent line. It's definitely going to be an issue that we, need to have the y value as well. So again, for one more page, I'm still going to try to avoid doing this thing called implicit differentiation. And here's my last ditch effort to try to avoid it. So I've got this same circle x minus 2 squared plus y plus 3 squared equals 5 squared, 25. And they're like, yeah, go ahead and find the slope of the tangent line. Okay, that's what they want here, right? They're saying, please find slope of the tangent line. Great. Well, right now, this relationship that's being given to me, the way it's being offered to me is what we call an implicit relationship. It doesn't have the form of y equals. So if I want to avoid implicit differentiation, I have to get it into an explicit relationship. I have to make it say y equals. So I'm going to say here, solve for y. Yeah, if you can. And for maybe one more page, for this page here, I will be able to. But then after that, I won't. So we'll need to have a plan. Okay, here goes, solving for y. How about we leave the y plus 3 squared on that one side, and then we can move the other x minus 2, so we'll have 25 minus x minus 2 squared. Okay, great. Now I'm going to go and take a square root. But I know the deal, when you go and take square roots, there's an issue with there being a plus or a minus. So right now I have this problem because I don't really know, like, should it be the plus or should it be the minus version when I actually go and do this root of all this algebra. By the way, all the algebra needs to be under one root. There's no option to say, oh, let's split it up into two roots, because then we can like root the 25 and root the x minus 2 squared. Yeah, that doesn't work, right? That stays like that. But we have this huge issue right now of asking ourselves, which is a big decision, which branch? Do you want the positive version? Do you want the negative version? I don't know, like, which one should it be? So you go and you look back at where this question's asking you to find the slope. It's at 5, -7. Let me just try graphing both of these things and see how they look. So I've really got two options for graphing. I could say, okay, how about, if I move this 3, it would be a -3. So -3, maybe it's the positive, maybe it's the plus root of 25 minus, in brackets, x minus 2 squared. Close the root. I don't know, let's try zoom 6 for a minute. Okay, that's the top half of the circle, and it looks absolutely horrible. And then here will be the bottom half. If I was to go -3 with the minus version of the root. We'll talk in a minute about why it looks so horrible. I missed a bracket. There we go. Let's make this bottom version a little thicker just so you can see it. Okay, here comes the bottom part. Well, that looks more like a football than it does actually a circle. How about we try zoom 4? We might have to zoom out a bit. That looks a little more circular. Okay, zoom out, please. Okay. Yeah, okay. Well, this point, 5, -7, is on the lower branch. It is on the minus version. So if I'm going to do this question, if I'm going to try to fight this implicit differentiation as long as I can, I will have to make a choice to choose the lower branch. Going back to zoom 6, the reason why it looks so bad and doesn't even connect them, it's just a calculator error. I mean, they really should touch, but if I trace along here, look at the awkward x values that it's actually evaluating the functions at. And at some point, I get to x is equal to 6.59 and has a point. At 6.80, it has a point. And then the next x value is 7.02. So unfortunate, it's just past the circle. If it had just tried figuring out what was going on at 7, if I say, hey, calculate a value at 7, then it's like, oh, well, that's right here. It's like, well, why didn't you draw it there? It's like, oh, I never even checked that pixel, because I only checked 6.8, and then I noticed 7.02 wasn't working. So purely a calculator error. Just watch out for that. In any case, for this story, if you're going to choose to do that -7, right, if you notice that, oh yeah, look where we're going to be working, then you have to go and make this choice to pick the negative version. So you would say y plus 3 is equal to the negative choice, right? If that's the branch you want, 25 x minus 2 squared. And you saw as I was putting it into my calculator, I actually moved the 3 and said negative 3. I think I did, didn't I? Yeah, I was putting the negative in. Worried there for a minute. Minus the root. Okay, just the bottom branch. I was lucky that I was actually able to solve for y, and then I had to make a decision along the way. The fact that I could solve for y means that I have created this relationship, this function that is explicit. And that's the kind of calculus we've been doing so far, where it says, here it is, it's right in front of you, y equals. That's the stuff we could do our derivatives with. So let's go ahead and try this out. I'm going to do my y prime for that. This will be the last time I can do this on this lesson, where I can actually do explicit differentiation. Y prime of x, otherwise known as dy dx. Okay. Derivative of negative 3 would be 0. Let's not even waste our time writing that. And then this stuff comes in here, this minus root. Okay, so minus, there's just a big blob there, right? Good thing we've done the chain rule. Okay, so minus the 1/2 comes down, leave the blob, don't touch it. All to the negative 1/2. That was cheating. I just treated that stuff inside as if it was x. Now let's go and do a derivative of that. Derivative of 25 is 0. And then, I'm going to do a chain rule here too. So how about negative 2 x minus 2 all to the first power. Derivative of that is a 1. Kind of wasting our time with that, but there we go. Okay. Wow. That was a mess. You could spend a lot of time tidying it up. Like, hey, look, this negative and a half and the negative 2, they're going to reduce. But why clean it up if you're only going to use the thing once, right? They're like, yeah, please go and figure this out at that point, 5, negative 7. Now, I know I'm on the right branch for the negative 7. So with this explicit approach, I only need the 5. I just need to know the x value. I've already chosen the right branch, the lower branch of this circle, so I don't need to know about that negative 7. Okay, putting numbers in. I'm going to have my negative 1/2. Got 25 minus 5 minus 2 squared. All to the negative 1/2 times a negative 2 times 5 minus 2 times a 1. Ooh, what do we got here? We have a negative 1/2. 5 minus 2, that's a 3. Squared is a 9. 25 minus 9 is a 16. So 16 all to the negative 1/2 times a negative 2 times a 3. Well, the 1/2 and the 2, they go away, so do their negatives. That 16 to the 1/2 is a root of 16. It's a 4, and it's flipped upside down. So we have a 1/4 multiplied by a 3. Okay, here's my answer. Positive 3/4 should be the slope of the tangent line to the circle at that one spot. Absolutely awkward to do it that way. We need a better plan. But looking back, yeah, okay, that seems right. The slope of that red line, it's not quite 1 over 1 up, 1 over and only 3/4 up. So yeah, it looks like we've got the right answer. But there's got to be a better way to get this to work. And there is, and it's called implicit differentiation. And we'll take a look at how to do that. But before we do, we just have to practice a little maneuvering first. Okay, so we're just going to work inside this box. And then when we've got this figured out, then we'll be ready to do the process of implicit differentiation. So we're just going to do some derivatives. The first one's super easy, right? What's the derivative with respect to x of just x, just 1x, right? What's its derivative? Well, that's super easy. It's just 1. What about the derivative with respect to x of x cubed? Well, not much harder, right? X is the variable. We're doing our derivative with respect to, we're going to have 3x squared. Okay, so the key thing here, I'm just going to write this in. This is the variable of differentiation. And I'm talking about this part right here. Okay, now it gets interesting. It's like, okay, what's the derivative of y with respect to x? Again, x is this variable of differentiation. So I can't just say, oh, that's a 1. That would be the derivative of y with respect to y. But this is saying, no, do the derivative of y with respect to x. Well, that's just what we've always called the slope. You know, that is this. That is dy dx. Or if you're Newton, that is y prime. That is the slope. And that's what we want to be going after. Okay, so when you start to do this at the bottom of the page, just realize that we really want that. Okay, that's the thing we're after, this dy dx. Along the way, we might find ourselves doing the derivative of y cubed with respect to x. So the variable of differentiation is this x, but then this blob on the inside says, look at me, I'm a y cubed. Okay, well that's a little odd. Let's do the chain rule with that. Why don't we go and say, well, hey, let's do the derivative with respect to y. Let's use y's as the variable. We'll follow the pattern, and then we'll multiply by dy dx. So whenever you do this, where you're taking a derivative and you're playing with y's, you'll see this kind of thing happen. This will be 3y squared, but that's not right. That's the answer if this had been a y, and it isn't. It's an x. So we'll just fix it. We'll multiply by the derivative of what we were cheating with, which is a y, with respect to what we should have done, which is an x. So you end up multiplying that by dy dx, which again is what we want, right? Now another way to write this would be to say, hey, can I write this as 3y squared times y prime? And you can, but just don't make your primes look like 1s, right? Make sure they're very clear looking apostrophes if you're going to do this. Derivative with respect to x of 4y, no problem. What's the derivative of 4y? Had that been like an x, well, it would have been 4x. That would just be a 4. And then multiplied by dy dx. Or if you wish, okay, just another way to write that, just be careful with your apostrophes. You could say, hey, that's 4 times y prime. Product rule. Okay, here we go, product rule. Derivative of the first thing, derivative of x squared would be 2x. Multiplied by the other thing, left alone. Don't touch it. No chain rule, no blob. I didn't do any derivative there. Just leaving the y to the fifth. But then you would add, now let's reverse. Leave the x squared. But now right here, I want to write down the derivative of y to the fifth with respect to x. So first of all, I'm going to cheat and say, well, how about we go with 5? Y to the fourth, but you just did a derivative with respect to y. That's totally fine as long as you fix it by multiplying by a y prime. So whenever you find yourself playing the pattern but doing it with y's, you'll always see a little y prime kicker come in on the end. All right, with that said, we are now ready to go. We're going to do some implicit differentiation of that same circle, and we're going to do the same point, 5, -7, okay? Also, again, worth noting this. Okay, this is quite important for today. Note, we need a pair. Oops, I need to learn how to spell. There we go. We need an x, y pair of numbers in order to know what to do later. Okay, two-step process. That's it, just 2 steps. First step, take the derivative with respect to x of both sides. So again, notice that x is supposed to be the variable of our differentiation. All right, so there's my relationship. It's implicit right now. It doesn't have it solved for y. And I'm going to go and take the derivative with respect to x of this side. And I'm going to take the derivative with respect to x of this side. Okay, so derivative of that, well, that's like a blob squared. So we're going to have 2 times the blob to the first power times the derivative of the inside. That would just be a 1. Okay, boring, kind of wasting your time there. Moving down the road. Y plus 3 squared. Well, it's a blob, so we're going to have, 2 blob to the first power. Now, what's the derivative of the inside? But don't say 1, right? It's kind of like a 1, but that's cheating because you use the pattern based on y's, and we're supposed to use x's. So it's 1, but then multiplied by y prime. And we want that, right? That's the thing that we want. So I'm actually happy that this thing has shown up to the party. That's your goal, is to get that. Okay, the other side. What's the derivative of 25? Easy, 0. Step 2, solve for that red thing. Go after that y prime. Just move stuff around until that y prime is all by itself. And so it's literally this easy. Let's tidy this up here a little bit. We have 2 times, I'm going to go with this part, y plus 3, y prime. Let's keep that on this side, is equal to negative 2 times x minus 2. I'm not even going to distribute the brackets open because I might not need to. Solving for y prime. Because remember, I wanted that, right? Okay, worth pointing this out, right? You want this. That's why we're solving for it right now. Y prime is equal to, okay, what do we have here? We're going to have negative 2 sitting on top of x minus 2. Sorry, negative 2 times x minus 2 sitting on top of 2 times y plus 3. Don't need the 2's. We're going to have a negative x minus 2 sitting on top of y plus 3. You can leave it like that, or if you wish, you can distribute the negative. Some people might, and say, here's my answer, 2 minus x, all sitting on top of y plus 3. There's my derivative. That's what y prime is. Now, this question originally said, please go and figure it out at the point 5, negative 7. So sure, yeah, okay, we'll do that. Got lots of room right here. It's going to be quick. So at this pair, 5, negative 7, so we have an x value and we have a y value. It looks like this derivative, y prime, is equal to, okay, putting numbers in, going right here, we're going to have a 2 minus the x value, minus 5, sitting on top of y, negative 7, plus 3. Okay, so that's a negative 3 sitting on top of a negative 4. Oh yeah, we're there. We're right where we were a minute ago. 3/4. Now, if we just eliminate all the little talking that I was doing there, this should be a much faster process. We'll be able to do these implicit differentiation deals really, really quickly. Let's try a whole bunch more out, see how they go. Number 5, find the equation of the tangent line to the circle at that point. So yeah, there's a circle out there, right? Looks like this, great. And then somewhere out there is this tangent line, and we'll see what the equation for that is. And this thing's going to be at the point 3, negative 4. So I don't know, it's got like some sort of tangent going to it like that. Okay, well, let's just do our implicit differentiation. So we're going to do a derivative with respect to x of both sides. Of this side and of the other side. Boring here, right? Just a 25. Okay. On the left, derivative of x squared with respect to x. Easy. Did that on the first day of the chapter. Derivative of y squared with respect to x. I don't know. Cheat. Do it with respect to y. Pretend y is the variable. And you get 2y. But that was cheating. You just treated y as if it was the variable of integration. It's not. So we just have to do the chain rule and say, oh yeah, now you have to multiply by dy dx, which a lot of people just like to write as y prime with a very careful apostrophe, is equal to 0. You get a lot of zeros here when you do this. Okay, solve for y prime. So 2y times y prime is equal to negative 2x. Looks like y prime, if you ever want to know what the slope of the tangent line is, looks like the 2's are going to cancel. We're going to end up with just a negative x divided by y. Okay, well that's helpful. Let's go and do an evaluation for that slope of the tangent line at one very specific point. They told me about it. They said it's the point 3, negative 4. Okay, well that would be the negative of 3 sitting on top of negative 4. Okay, 3/4. All right, fantastic. That was quick. Now we're going to go and find the equation of the tangent line, because that's what they really wanted from us. Well, what I know is there is a point. The point is shared with the tangent line in the circle, and there is a slope. It's actually equal to 3/4. Played this game on the very first day of the course. This is easy. We're going to go y minus a negative 4 sitting on top of x minus a 3 is equal to 3/4. You just have to move the x minus 3. The equation of my line, y plus 4 is equal to 3/4 times x minus 3. I would not even bother simplifying that. There's just a risk of us making some sort of error along the way. That one's done. Okay, let's try number 6 out here. Again, I've got this mess, right? And it's not easy to solve for y. This is how you know that you're going to do implicit differentiation, is you look at it and you go, my gosh, there are y's all over the place. I'd never get that into a form of just y equals. No problem. We'll just do this two-step process of implicit differentiation. First step, take a derivative with respect to x both sides. So that's going to be 3x squared, just working my way along, plus 4y. Oh, I just cheated. So now I have to multiply by y prime. And then minus, oh, be really careful here with this. Okay, I'm going to deliberately make an error here just to show you what's going on. I've got a product rule. I've got that multiplied by that. Okay, so watch me make a mistake here. 3x squared, derivative of that, that's just going to be 6x multiplied by the other part just left alone, y cubed, totally fine. Then the product rule says add. Now leave the first part, 3x squared, and now do a derivative of y cubed. Okay, no big deal. Haven't made any real mistakes yet. So y cubed, let's just fake the pattern with y's. So 3y squared, that was cheating. I did the pattern with y's, it was supposed to be x's, so I'll add in a y prime. And that's great, except for the fact that this minus sign led this entire product. So my entire answer for the derivative needs to have this minus sign affect it, and right now it just doesn't. So what I need to do is just get my order of operations right and just put that on there. That way this whole product is affected by that subtraction. Okay, finishing this off, doing the derivative on the other side, super easy. Derivative of negative 2 is 0. All you have to do now is solve for y prime. So we'll get all the y prime terms on one side. So it looks like we have a 4y prime. This one's got a couple of y primes. We're also going to have, looks like minus 9x squared, y squared, y prime. Another one of the things we're looking for. Now dump everything else over to the other side. So we're going to have a negative 3x squared. And by the time it gets to the other side, it'll be a positive 6x y cubed. We want to get those y primes together into a single answer. So we're just going to factor it. Okay, we'll factor a y prime out. And we're going to have 4y minus 9x squared y squared. And it doesn't matter. It's personal preference. Do you want to factor the y prime out on the front, or do you want to factor it out on the back end? Right? It doesn't really matter at all. Some people like to write it like this. They can think of that as being a coefficient, that blue stuff in front of the red y prime. Okay, we are there. The derivative for this thing, the y prime, the dy dx, whatever you want to call it, right? So you can write it like this, you can write it like this, depending on whether you're Newton or Leibniz. Looks like it's going to be a big fraction of algebra, and as is completely typical with this implicit differentiation, it has x's and y's in it. So in order to evaluate this, come up with a slope for your tangent line, you would have to know an x and a y value. Now, one last thing with this one, if you were checking your work, as we always should, and you look at the back of the textbook, you might go, whoa, wait a minute, I got something wrong. Well, they might look at it and go, oh, you know what? It doesn't look nice with that minus being the very first thing in the top. Why don't we go and multiply everything in the top by a -1? So we'll have 3x squared minus 6x y cubed. And then we'll multiply everything in the bottom by a -1 too. Might be nicer to write it 9x squared y squared minus 4y. Just personal choice. They're both the same thing. Just whichever one you think, looks the nicest, right? Doesn't matter there at all. Okay, just a couple more to do. This next one is a little long. It's going to take the full page, so be careful with how much you write, or how big you write. Now we're going to find the equation of normal lines. Oh, be careful with them. Okay, normal lines are perpendicular lines, right? To the ellipse at the place where x is equal to -1. Okay, well I see -1. Yeah, you're right here. Oh, whoa, hang on. There's one point here, and then there's another point here where x is equal to -1. It looks like there are two places where we're going to have some normal lines. Now we're going to have to be super cautious about that. We've got one normal line going in here, perpendicular to the ellipse, like that. And then there's another one that, oh, it looks like it's super steep. It looks like it's kind of like this, right? And we have to find both of the equations of those red lines. It's got twice as much fun, right, in the one question. So let's first go and find those y values. Okay, that's going to be my first task. You might say, hey, I'm going to see them right off the graph. Well, if the graph is clear, what if it wasn't? So let's just be careful here. We're going to put -1 in for x into this equation. So I'm just taking this equation here, but putting -1 in. So I would have -1 for x. So if I want to talk about y values and x values, I use the original equation. So I have 1 plus y plus y squared is equal to 7. Quadratic, no problem. Y squared plus y minus 6 is equal to 0. Y plus 3. Y minus 2 is equal to 0. Okay, I got a couple of y values for you. We've got y is equal to -3 or 2. Yeah, okay, it looked like what we saw in the graph. So we've got a couple of points here. One point right here is -1 for x because they said so, and 2 for y. And the other point here, -1 for x because they said so, and -3 for y. All right, let's go and do some implicit differentiation. Let's go and find the slope of some tangent lines. Now, I know you might be thinking tangent lines, we don't want them. We want normal lines, right? But the only thing calculus is good at is tangent lines. So we'll have to work with tangent lines first, and then go and flip that around and look at the slope of those red normal lines. Okay, implicit differentiation. Taking a derivative with respect to x for that right there. All right. Working just across from left to right, we're going to have 2x. Oh, product rule, be careful. So we're going to say minus, but let's lead in with a bracket here. Derivative of x times the y left alone, so just like 1y, and then plus, leave the x, the derivative of the y, that would be y prime. And all of that's led by the subtraction, plus 2y, I just cheated, I did the pattern using y's, so now I have to put in a y prime, and then the derivative of 7 is just 0. Okay, time to solve for the y primes. See what we have. Looks like we're going to have a negative x y prime. I'm going to keep all the y prime terms here. The rest are leaving. What other ones have we got? Oh, plus a 2y y prime. And now all the other terms. Let's bail them out here. We'll have a y minus a 2x. Okay, well, you guys have seen what happens, right? We're going to factor and then dump the binomial over to the other side. We're running out of room here, so let's be efficient. Looks like the derivative, it's going to need x and y values in order for you to figure it out. It's going to be y minus 2x, all sitting on top of, well, I'm going to write this 2y minus x, just to keep everything leading off with a positive. Okay, that's handy. Going to need that now when we go to finish this off. We're going to find the equations of those normal lines. I'm going to split my page here because I've got 2 questions to do. All right, let's just go point by point. First point that I want to try is the point -1, 2. So let's go and find out what y prime is doing there. So I'm just going to go and drop in those values using what I've got there in the box. 2 for y minus 2 times a -1. Then in the bottom, 2 times a 2 minus a -1. And when you clean that up, you end up with 4/5. But be so careful because that is the slope of the tangent that's there. And this question was just trying to throw us off. It said, no, you got to go and find the normal line. Okay, well, let's do these things in parallel as we work down the page. What about the other point? What about -1, -3? It's got a different slope to it. Slope of its tangent line, have a -3 minus 2 times a -1, and then in the bottom 2 times a -3 minus a -1. That one ends up being, well, it's like -1 on top of -5, so it ends up being 1/5. But once again, that's the slope of the tangent line. Now, I don't know what color I used up above. Let's take a look. Yeah, those are the pink tangent lines that are there. We don't want those. We want those red normal lines, right, that are perpendicular to that. So we're going to make a little change here. Let's do it right now. So we want things that are perpendicular to that. So the normal slope, the perpendicular line slope, this is going to equal -5/4. And for this point, the line that's perpendicular to the graph, we just call it the normal. Again, we're going to take this, spin it around a little bit. That'll be a -5. Okay, now we're back to the very, very first day of the course. Super easy. We've got a point, we've got a slope in each of these stories. So we're going to say y minus 2 sitting on top of x minus -1 is equal to -5/4. Tidying it up, we've got that required move to move the binomial, but don't do any other distribution. It's not worth it. There's one perpendicular line, one normal line, and then the other one. Y minus -3, all sitting on top of x minus -1, has to have a slope of -5. Y plus 3 is equal to -5. times x plus 1. Two different lines, two different spots where we have that normalcy. And that's going to take us to our final page, where we're going to look at second derivatives. How do you find the second derivative of y if you're playing this game implicitly? It's actually not too bad. We'll do a couple of examples here. First one, see if you can find the second derivative for this relation. It looks like a circle of radius 8. Okay, and we'll see what happens for y double prime. All right, well, I get to y double prime by first doing a single derivative and get to y prime. I'm going to do it implicitly. And I'm going to have, working with this relationship here, I'm going to have 2x plus 2y times y prime, first derivative, is equal to 0. Okay, so far so good. Looks like 2y times y prime is equal to negative 2x. Remember, we want that red thing, right? It's what we're trying to get to. So it looks like that red thing, that first derivative, get our colors right here, cancel our 2's, we're going to have a negative x on top of a y. Okay, well that's not the answer, but we're close. Okay, that's the first derivative. We just need to do one more derivative and then we're there. When we go to do the next derivative, be aware of the fact that what we're staring at here right now is a quotient. So we're going to have to very carefully do the quotient rule. Right, we're looking at something divided by something. All right, here we go. Y double prime. Let's just do a derivative of what's in that box. So yeah, quotients are never fun, but they're doable. Right? We're going to have that's equal to, okay, derivative of the top. Derivative of the top is going to be negative 1 multiplied by the bottom left alone. Okay, subtract, leave the top, and then the derivative of the bottom. Well, the derivative of the bottom, it's a y, so its derivative, well, this is our usual game, right? Derivative of y would be y prime, first derivative. And then you divide all of that by the bottom squared. Okay, so far so good, except one issue. When we go to evaluate things like this second derivative of y, we want to be able to put x's and y's in. And I'm seeing, you know, if I look, I'm seeing x's and y's here, but then there's this big red thing, and I don't want that. So I want to be able to, when I'm done, have something that's good for just x's and y's. So we're going to go and do a little substitution. Okay, let's just offer in what we know y prime to be. So we're going to have this. We're going to have negative y. Now I guess this is going to be plus an x multiplied by those negatives cancel, right? And then, oh, well, what is this y prime? It's right here. It's actually negative x on top of y. Ooh, it's getting a bit messy. And all of that's on top of y squared. So all I did is just some substitution. That way this thing that I'm finished with, well, I'm almost finished with it, has nothing but x's and y's in it. I really don't like the way it looks though. It's got fractions inside fractions. So let's play our usual game here. Let's give the very top of this fraction and the very bottom of this fraction, let's give them a little nudge, a little kick. Let's multiply them both by y. That'll make it look more and just nicer. So I'm thinking that this could look good. The second derivative of y, okay, as I distribute this y, and it's going to distribute to both sides of this plus sign here, we're going to end up with a negative y squared as that distributes. It cancels here, so minus an x squared, all sitting on top of a y cubed. And that's a very legitimate answer, but it turns out if you check the back of the book, you probably won't see that, and you might be going, what is going on? Well, just watch this. This is very, very common for second derivatives. You can do a little more cleaning up. Maybe we'll factor out a negative, I'm going to factor out a negative 1, and then I would have x squared plus y squared, and all sitting on top of y cubed. Now we're going to do something that's called back substitution. Here's the thing. Take a look up here. X squared plus y squared is apparently equal to 64. So this is a nice little spot where I can put that in. X squared plus y squared. Hey, you're in this question, maybe not every day in every question, but in this question, I can tell you that x squared plus y squared is actually equal to plain old 64. So why not write this like this? Second derivative, this is just going to be, I got my negative 1 there, so a negative 64 sitting on top of y cubed. That just looks a little cleaner. Turns out I don't even need to know what the x is. I just need to know what the y is in order to get this to work. And so that maneuver right there is sometimes just called back substitution. I get my pen to work. Come on. There we go. Yeah, so what we just did here, good old back substitution. Final one. Let's see if we can find the second derivative for this relationship here, and we're going to evaluate it at 1, negative 3. Okay, this might give us a chance to try out some of that substitution. Let's see if this thing cleans up. So at the beginning, we do our first derivative. We're going to do it implicitly because I can't get those y's by themselves, not easily. And so I would end up with 2y. I was just cheating with that, so that picks up a y prime. That's okay. I kind of wanted it to come to the party. Plus a 2y prime. Oh, shows up twice to the party. Is equal to 2 plus 0. Ah, just that. Okay, a lot of 2's I don't need. I could cancel those 2's. Do a little factoring here. That's reduced by 2. And then we'll have y plus 2 multiplied by y prime is equal to a 1. Oh, sorry. If I'm factoring a 2 out, I didn't do that right. Cancel the 2's, then factor. Okay, like that. So solving for y prime, I'm going to have a 1 sitting on top of a y plus 1. Okay, we're close, right? There's the first derivative. We're supposed to go one more down the road, and then we're supposed to actually evaluate it. Okay, well, I think we can get there. All right, it's a quotient rule, unfortunately. This is often the case. Let's go and do y double prime. All right, derivative of the top would be a 0 multiplied by the bottom left alone. Well, that was a waste of time. Now leave the top, 1, and then the derivative of the bottom. Well, I want to say 1, but that's using the wrong derivative. That's with respect to y, so I just cheated. So a little y prime is going to show up. And then we'll divide all of that by the bottom squared. Now, obviously, this is 0, right? That's gone. And so what do we have here, right? This is going to be basically just a minus y prime, all sitting on top of y plus 1 squared. Okay, well, that's going to be a complex fraction, but I know how to deal with those. We're going to have the negative of, let's just insert this in for y here now. Y prime is 1 over y plus 1, and that's sitting on top of y plus 1 squared. Okay, our usual little complex fraction game. Let's give this a little nudge, top and bottom, we'll be fair, with a y plus 1. This is going to look a little nicer. How about negative 1, all sitting on top of y plus 1 cubed? Almost done, except they're like, oh, can you please go and put this point in? Can you please go and figure out your second derivative at the point? And they're requesting 1, negative 3. I don't even need to know about the 1, actually, in this particular problem. I can actually just say it's going to be this easy. Negative 1, we'll just take the y. Negative 3 plus a 1 cubed. Okay, so a negative 1 sitting on top of a negative 2 cubed. We've got a negative 1 sitting on top of a negative 8. All right, 1/8. And that one's done. Didn't see any back substitution show up in that one. That would have made things easier. So yeah, second derivative, get your first derivative straightened away. Don't put your values in yet, right? That point, 1, negative 3. Wait until you've done your next derivative. Do some substitution there, right? Which is what we did when we dropped in this y plus 1 right here. And then you're good to go. And that's what we do with implicit differentiation. It's something we do whenever we see y's embedded in the question all over the place, you know, like we had right up here, right? When you see just a mess of y's, no problem. Just take a derivative of both sides just in place and then solve for the y prime. And that finishes up our lesson.